Hello and welcome back to Power Series Part 2. Previously we looked at how to find a interval of convergence for a power series. So we looked at a power series and said for what values of x does this series converge? To do that you use the ratio or root test, or sometimes the geometric series test, to find an open interval of convergence, and then you have to test the endpoints. So now we're going to list some theorems and do some examples of how you can combine power series and how you can manipulate them, what operations are valid on them, and how do you go about doing these operations. So the worst theorem that we're going to talk about is the multiplication theorem. And I'll put in parentheses, this is for power series, because, there's probably more than one multiplication theorem out there. So if a of x is the power series an x to the n, and b of x is the power series bn x to the n, and if both of these converge absolutely for the absolute value of x less than r, and if we define Cn to be a0 bn plus a1 bn minus 1 plus ... plus an b0, which is the summation from k equals 0 to little n of ak b sub n minus k, then the power series Cn x to the n converges absolutely. It converges absolutely to a of x times b of x. And it converges for the absolute value of x less than r. So it has the same radius and interval of convergence. And all of this is saying that if you want to multiply power series, so you have the power series an x to the n times the power series bn x to the n, the way you're going to get those coefficients is you're going to do this Cn that is above. And this gets really messy really quick. This is really disgusting. All of this is to say, hopefully you never have to multiply power series. So next theorem that we're going to talk about operations on power series. If the power series an x to the n converges, say it converges absolutely for the absolute value of x less than r, then the summation of the power series an f of x to the n, this also converges absolutely, as long as f of x is a continuous function. And it has radius of convergence and interval of convergence, absolute value of f of x less than r. So in other words, if you have a power series, you can replace x with some continuous function on x. So an example of that. We know that the power series x to the n converges for the absolute value of x less than 1. How do we know that? This is exactly a geometric series. And we know what this geometric series sums up to. We know that it converges to 1 over 1 minus x. So really what we're saying is that 1 over 1 minus x equals this infinite polynomial. So if we wanted to find 1 over 1 minus 4x squared, well, this is exactly replacing x in 1 over 1 minus x with 4x squared. So all we have to do is replace x in the power series representation with 4x squared. And this also converges for the absolute value of 4x squared is less than 1. Cool, so we can replace x with any continuous function. What else can we do? We can also differentiate and integrate of power series. So suppose that f of x is what the power series Cn x minus a to the n converges to. And suppose that it has a radius of convergence r greater than 0. Then, first, if you wanted to differentiate that, then you would have the sum, the power series, from n equals 1 to infinity. So I should really put where we're starting, n equals 1 to infinity. N equals 0, sorry. N Cn x minus a to the n minus 1. So emphasizing here, when you differentiate the power series, all we're doing is we're differentiating it term by term. But when you differentiate the constant term, you get 0. So we're going to lose the constant term. That's why we go from starting at n equals 0 to starting at n equals 1. And b, the integral of f of x dx is c plus the power series starting from n equals 0 to infinity of Cn divided by n plus 1 times x minus a to the n plus 1. Again, all this is really saying is that when you integrate, and same with when you differentiate, you do this term by term. So big caution here. Haven't really emphasized this yet, but this is everything we're doing really is true for what I'm about to say. This only works for power series. The summation of n factorial cosine of n factorial x divided by n squared, this is not a power series. Yes, it has x's in there, but the definition of power series is that you are adding powers of x. You're not adding some random function of x, you're adding powers of x. And here you don't have powers of x. So just make sure whenever you see something that looks like a power series that it actually is a power series. So let's see some examples of this differentiation and integration. So let f of x equal 1 over 1 minus x. Find a power series for f prime of x. So the way we do this is we have f prime of x, by definition, is the derivative of 1 over 1 minus x. This is, assuming that x is less than 1, then we can write the power series representation for 1 over 1 minus x. That is the sum from n equals 0 to infinity of x to the n. And then we just differentiate this term by term. That means that's the sum from n equals 1, because we're going to lose the constant term, of the derivative of x with respect to x of x to the n. So the power series representation for the derivative of 1 over 1 minus x is n x to the n minus 1. Okay, next example. Find a series representation for f of x equals the natural log of 1 plus x. Now this one's a little bit harder because I didn't tell you how you're going to get your hands on this natural log. So, first we notice that the derivative of f of x is 1 over 1 plus x, which is 1 over 1 minus a negative x. And the power series representation for this is the power series representation of 1 over 1 minus x, but evaluated at negative x. So we'd get negative x to the n. We want the power series representation of f of x, not the derivative of f of x. So we integrate. Fundamental theorem of calculus says that if we integrate the derivative of f, we will just get f of x back. So this is the integral following all the way through. This is the integral of the sum from n equals 0 to infinity of negative x to the n dx. And if you want to be pedantic, this is the integral from 0 to x. The theorem that I said that we're going to integrate this term by term. So that is the same thing as saying the sum from n equals 0 to infinity of the integral from 0 to x of negative x to the n dx, which is the sum from n equals 0 to infinity of add 1 to the exponent, you get n plus 1, and then divide, you get negative x to the n plus 1. And then you had to do a u substitution because we have negative x in there. So we have to multiply by negative 1. In other words, that negative sign is coming from dx is negative du. So that would be our power series representation for the natural log of 1 plus x. And we know that this also converges for the absolute value of x less than 1, because that is what the interval of convergence is for 1 over 1 plus x, because that is what the radius of convergence, interval of convergence is for 1 over 1 minus x, when you replace x with a negative x. Okay, 2 more examples. What function is equal to the series summation from n equals 0 to infinity of negative 1 to the n x to the 2n plus 1 divided by 2n plus 1. And let's label that f of x. Okay, solution. So what we're going to want to do is we want to manipulate this to look like a power series that we know or somewhat know. So first what we're going to do is notice that f prime of x, if we were to differentiate this, this is the sum from n equals 1 to infinity of negative 1 to the n, x to the 2n. Okay, but this, we can bring that negative 1 inside. This is the sum from n equals 1 to infinity of negative x squared to the n. This looks like the sum from n equals 1 to infinity of y to the n, which we know, running out of space. Let me maneuver some things. which we know this series is 1 over 1 minus y. So that means that f prime of x is 1 over 1 minus negative x squared, which is 1 over 1 plus x squared. So if we wanted f of x, now we just integrate. So f of x is the integral of f prime of x dx, which is the integral of dx over 1 plus x squared. This is a well-known integral. This is tan inverse of x plus c. So now we need to figure out what this plus c is. Going back to what our function is, f of x equals this. If we evaluate this at 0, then we get 0, but then we have that n equals 0 term, which is going to be a 1. But when you plug in 0, when n equals 0, the first term is going to be, you're going to have a power of x, because we're taking all the odd powers of x. So let me write out what I'm saying, because I feel like I confused myself. The first term would be x divided by 1. The next term would be negative x cubed divided by 3. Third term would be positive x to the 5th divided by 5, etc. And key thing here is the first term is not constant. So when you evaluate f at 0, you get 0. So using that here, we have 0 equals f of 0 equals tan inverse of 0 plus c. Tan inverse of 0 is asking tangent of what equals 0, which is where does sine equal 0 and cosine not equal 0, and that is at 0. So we get that c equals 0. So f of x was tangent inverse of x. The function that has power series representation, this, is tangent inverse of x. Last example. What function is equal to f of x equals the summation from n equals 1 to infinity of x minus 5 to the n over n? So I'm going to let you do this. I recommend pausing the video, doing this, and then unpausing the video to see how well you did. So first thing we want to do is we want to get rid of this n in the denominator, because that's kind of weird. So if we differentiate, you get f prime of x equals the summation from n equals 2 to infinity of x minus 5 to the n minus 1, which is the summation from n equals 1 to infinity of x minus 5 to the n, which is 1 over 1 minus x minus 5, which is 1 over 1 over 6 minus x. Undo that differentiation. So f of x equals the integral of f prime of x dx equals the integral of dx over 6 minus x, which is negative natural log absolute value of 6 minus x plus c. Since f of 5 equals 0, you want to use the center here. Center is 5. We have 0 equals negative natural log absolute value of 1 plus c, so c equals 0. So f of x equals negative natural log absolute value of 6 minus x.